Institute of Engineering and Technology.
Hello students, today in this discussion we will try to cover two more tests to check whether series is convergent or not. Our main focus will be on how to find convergence or divergence of any infinite series by remaining in series only. We have seen many different possibilities or many different theorems to check whether given series is convergent or not. Let me recall all such tests and then we'll continue towards our today's two different tests. We have seen what do we mean by nth term divergence test. We have also seen comparison test, in which we are actually comparing two different series. Then we have seen ratio test, which is also known as D'Albert's ratio test. In D'Albert's ratio test, we are considering two consecutive terms of given single series. And we have seen in many different possibilities, ratio test is not actually useful. The test fails whenever ratio is equal to 1 at infinity. Today our attempt is to consider one extension of a ratio test, which is also known as Raabes test. And we'll also go through one more possibility or one more test, which is Cauchy's root test. So in this case we are considering again single series and we are considering two consecutive terms or single term at a time. Also we know now what do we mean by absolute convergence. So we'll also try to incorporate this absolute convergence through these two different series. So let us start our first part, which is in chapter of infinite series, and it is Raabes test. So if I consider the concept of Raabes test, it is something like this. So the first point is Raabes test is actually extension of our regular D'Albert's ratio test. Now if I recall at this point, what do we mean by ratio test? In ratio test actually we are taking two consecutive terms from infinity and then we are checking whether they are following our rule of convergence or not. The rule of convergence is whether the existing term is bigger than upcoming term or not. It simply means that term by term our series must be decreasing its value and they must move towards 0. So this Raabes test is somehow defined in this way. If I consider series un of positive terms and there exist three different constants c, k and capital N, such that un upon un plus 1, again I am taking ratio of two consecutive terms, is exactly equal to 1 plus capital C upon n plus f of n upon n square. Here capital K is in such a way that mode of f of n is strictly less than k for all n greater than or equal to n. The meaning of this statement is, if I take two consecutive terms, again they are exactly equal to a finite quantity after certain values of index capital N. But now to understand this thing or how to relate this thing with the convergence of our given series, we need to focus only and only on one component from this three, which is capital C. So if we have this ratio condition and if our capital C is greater than 1, then and then only we can say our given series is convergent. Whereas if this capital C is less than or equal to 1, our series is going to be a divergent series. Now this test or this condition 1 plus C by n plus f of n upon n square is quite difficult to calculate in general. So we will try to mold this condition for students in such a way that it is easy to calculate, and again we can conclude with this new condition. So if I focus on this part, which is I am redefining a same theorem, that is, if my series is positive term series and limit n tends to infinity n times in bracket un upon un plus 1 minus 1, if this is equal to capital L, then we can say if capital L is greater than 1, this given series is convergent. So somehow this is pretty much close to our regular ratio test in form of condition. See here, again I need to consider a term which is depending upon ratio, but now it is slightly defined in a different way. In place of un upon un plus 1, it is un upon un plus 1 minus 1, and then it is multiplied with small n. And if that limiting value is given by L, upon value of L we can say whether given series is convergent or divergent. But here again the constraint is if this L is equal to 1, this test is not going to work. This test is failed, and if test is failed, that doesn't mean that series is divergent, it simply means that we need to go for some another case or some other test. Now let us see how we can incorporate our absolute convergence using Raabes test. So if I consider any series summation un, any series means now we are not restricted only up to positive term series. This can be any series with negative terms or combination of positive and negative, which is also known as alternating series, which we'll see in future. So if this series un is any random series, then I need to consider our regular test of Raabes condition, but now in place of considering our regular term, I am taking magnitude of this n times un upon un plus 1 minus 1, which is again resulting into n, and then the condition is same. The only difference from our regular convergence to absolute convergence is magnitude of condition. Now let us see example of this Raabes test. Suppose we have this infinite series defined by 2 by 7 plus 2 into 5 upon 7 into 10 plus and so on up to 2 into 5 into so on up to 3n minus 1 upon 7 into 10 into so on up to 3n plus 4 plus and so on up to infinity. So this type of infinite series are quite difficult to handle by any of our regular tests. The reason is the terms are itself increasing by values from numerator and denominator with index n. So now how to deal with convergence or divergence of such series? So in solution, I need to consider first of all an upon an plus 1. So what I will do? I will take an as our regular term in the given series, and then I will replace everywhere n with n plus 1. So now if I replace n with n plus 1 in 3n minus 1 in numerator, n is replaced by n plus 1, so it is 3n plus 3 minus 1, so it is 3n plus 2. In denominator it is 3n plus 3 plus 4, so it is 3n plus 7. But as it is in denominator, the values are in a reverse way. After cancellation, there will be only two terms, 3n plus 7 by 3n plus 2. Now if I take magnitude of this values, and if I take n tends to infinity on that, my value is equal to 3. and that means my ratio test, my regular D'Albert's ratio test is not working in such case. So now whenever your ratio test is failing, you should always check its extension, which is Raabes test. So in this case, now I am going to consider our second part, which is Raabes test. So here I am taking n times a n upon a n plus 1 minus 1 with n tends to infinity. If I simplify this numerator, it gives me 5 upon 3n plus 2 multiplied by n, and then in denominator I am taking n outside, so it will result into 5 by 3. If I take this value 5 by 3, then it is greater than 1. This simply means that by Raabes test, this series is convergent. So now remember, whenever your whenever your ratio test is not working, you should always check at least once about its extension, which is Raabes test. Now let us go for our second part of discussion, which is root test. If I consider summation n from 1 to infinity un as a series of positive terms, and if I take a condition limit n tends to infinity with the nth root of un equal to L, then I can discuss its convergence and divergence. If this L is less than 1, then series is convergent. If this L is greater than 1, the series is divergent. And again, the constraint remains over here also, that if L equal to 1, this test is going to be failed. Now if you look carefully, the whole path of considering convergence is now reduced at a single term of the given series. If I recall, we started with comparison test, in which I am taking given series and it is compared with totally new series. If I take ratio test, in ratio test we are taking two consecutive terms of the series, and then in extension also in Raabes test we are considering two consecutive terms. But now Cauchy made this work very easy by considering only single term un at a time from this series, and by taking its nth root, and it is limited value at n tends to infinity by L, will decide whether a series is convergent or divergent. So in this way, the role of convergence and divergence is very reduced to a single point. Now how to use the same test in case of absolute convergence? For example, if I want to check whether my given series, now it can be any random series, is convergent or not using roots test, then in root test now I need to take nth root of mod of un. So the only change from our regular test is now it is magnitude of un, and that is again equal to L. So now if this L is less than 1, we can say it converges absolutely. If L is greater than 1, it diverges. But if L equal to 1, then test fails. Now let us see one example of root test. For example, if I have series n from 1 to infinity n square upon 2 raised to n, and if I take an as n square upon 2 raised to n, then its nth root is given by with limit n tends to infinity by n square upon 2 raised to n whole raised to 1 by n. And then in next term, if I take this 1 by n separately in numerator and denominator, it will reduced to n raised to 1 by n whole square upon 2. Now this n raised to 1 by n with limit n tends to infinity is nothing but infinity raised to 0 form. And we have seen this indeterminate form in detail in our different talks of our indeterminate forms. Now if you solve this n raised to 1 by n, it will result into 1, and that simply means that my value is 1 square by 2, which is nothing but 0.5, which is less than 1. So clearly by this root test I can say that this series is convergent. So this was actually our talk on how we can incorporate conditional convergence also, absolute convergence in our regular different test. Today we discussed about root test, its extension. Today we discussed about ratio tests extension, which is Raabes test, and we considered Cauchy's root test. I hope all of you understand these two different tests for checking whether given series is convergent or not. And in upcoming lectures, we are also going to consider alternating series and its test for convergence, which is Leibniz test. We'll also see what do we mean by conditional convergence, and finally we'll see power series with radius of convergence. Thank you.
LJ Institute of Engineering and Technology.